Today we're going to continue our march through the hydrogen atom and trying to solve the energy eigenfunctions for our hydrogen atom. Just a quick sort of recap of what we've done. We've sort of just used separation of variables for this. Our eigenfunction for the hydrogen atom was first split into a wave function that involved just the center of mass coordinates and one that had involved the relative coordinates between the nucleus and the electron. We then did separation of variables again on that relative wave function there and separated it into a part that only depended on the radial direction and one that depended on the sort of angular part, right? And when we did this, we had to introduce sort of some constant a that came from this separation of variables process. We then did separation variables again and wrote this angular part of our wave function as two functions, one that only depended on the polar angle and one that only depends on the azimuthal angle. And in this case, we had to add another separation of variable constant, b, that we had to figure out. In the last video, what we did was we solved for this azimuthal part. We showed that azimuthal function phi was equal to 1 over root 2 pi e to the I, some integer m phi, right? So m equal to 0, plus or minus 1, plus or minus 2, any of those integer numbers, right? And this m, actually, if you look back and recall when we solved this differential equation, this came from root b was equal to m, right? When we had our original differential equation that solved that, this ended up being the solution. This was a root b, but it had to be some integer that we called m. So we've sort of sorted out this b now. And obviously, the more important part, we know what that azimuthal wave function is. What we're going to focus on today is solving for that polar part of our wave function. And if you can go through the other videos or your textbook, we can basically what that boils down to is solving for this differential equation. 1 over sine theta, the derivative with respect to theta of sine theta d theta, minus that separation of variable constant b times 1 over sine squared theta. That all operating on our polar function was equal to negative a times that polar function. So this is the differential equation we have to solve to figure out what that polar function is. To do that, what we're going to do is make a substitution. We're going to actually create a differential equation of some function of z that's equal to that polar function, and we're going to make this substitution z is equal to cosine theta, which means d theta is just equal to d dz dz d theta, and dz d theta is equal to, if we take that, it's just going to be negative sine theta, right? So we've got d theta is equal to negative sine theta ddz. Also, just, we have the trig identity that we all know cosine squared x is equal to sine, the cosine squared x plus sine squared x is equal to 1, so sine of x is equal to 1 minus cosine squared x, all square rooted. So we can write this derivative d theta in terms of our variable z, 1 minus z squared d dz. So if we make this substitution, we can sort of rewrite this differential equation in terms of our z variable and our function of z, and it ends up being, let's go up and just do it step by step. This is that sine we replace with 1 minus z squared. This dd theta becomes negative root 1 minus sine squared d dz, and that's acting on sine theta 1 minus z squared. Replace this dd theta with a negative 1 minus z squared d dz. How many brackets do I need here? One more, I think. Minus b 1 over 1 minus z squared, substituting that sine squared in there. All of this operating on our p of z function is equal to negative a function of z. This can be simplified, obviously. These cancel, these multiply together, and we end up with just dz operating on 1 minus z squared dz minus, if we sub in the fact that b is equal, or root b is equal to m, this ends up being m squared over 1 minus z squared. And if we wanted to, we can bring this over to the other side. So then this would be plus a, all operating on z equals 0. One more thing we can do is this first term here, we can apply the chain rule, ddz on this. It gives us negative 2z ddz. And then on the next term is just 1 plus z squared d squared dz squared, right? So if we do this term, it looks like that. So putting that all together gives us our final sort of differential equation, which is 1 minus z squared d squared dz squared minus 2z d dz plus a minus m squared over 1 minus z squared, all operating on our z function, equals 0. And this equation has a name. It's referred to as the associated Legendre equation. Not 100% pronunciation of the Legendre, but that's what it is. We can look at a specific case, right? If we look at the m equals 0 case, this term goes away, and we get sort of a simpler 1 minus z squared d dz, second derivative with respect to z, minus 2z first derivative with respect to z, plus a. This equation is called just Legendre's equation, and we can solve this just with a series solution. To do that, we essentially just assume that we take this p of z and say, all right, let's assume it's a power series from n to infinity of some constant a sub n times z to the n. We take that expansion, we plug it in, and sort of solve for what these a sub n coefficients are, and we have our function. So to do this, though, we're going to need, just looking at our differential equation, we're going to need to know what these derivatives are. So with that as our function, the first derivative with respect to z is just going to be a sub n times n z to the n minus 1, right? And the second derivative, we can do it again, 2 of p sub z is equal to, and hopefully we can all follow this, n times n minus 1, z to the n minus 2. So when we operate all those in there, what does our differential equation become, right? If we take this, substitute those, or plug in those differential equations, we have, well, the first term for this 1 here is just sum over n, a sub n times n minus 1, z to the n minus 2. The second term that includes this z squared is equal to minus z squared sum over n, a sub n minus 1, z to the n minus 2. The third term, this one, is minus 2z sum over n, a sub n times n, z to the n minus 1. And then this final a term is plus a sum over n, a sub n, z to the n. Right, and all this is equal to 0. If we bring in these z squared, multiply it inside this sum, it's going to get rid of that minus 2 in the exponent. This z is going to get rid of that minus 1. So this whole thing now becomes sum over n, a sub n minus 1, z to the n minus 2, minus sum over n, a sub n minus 1, z to the n minus 2 sum over n, a sub n z to the n plus a sum over n, a sub n, z to the n equals 0, right? One of the things that is going to be useful is if we can get all of these sort of sums to line up with, we're interested basically for this to be 0, all the powers have to be, all the coefficients for all the powers, all the exponents of the same power have to also be 0. So we want to look at this first term, and essentially this is going to be equal to a sub n, n equals 0 times 0 minus 1, that first term in that sum, plus a sub 0, a sub 1 times 1 times 0 times z, plus the sum over n equals 2, the rest of this series, a sub n, n minus 1, z to the n minus 2, right? That's what this first term equals. Well, these two are obviously just 0, so that first term can actually be written as n equal to 2, summing from 2 to infinity of an n minus 1, z to the n minus 2. This indice, this n, is just like an index. It's a variable, so we can shift it by 2, and this ends up being sum over n equal to 0 to infinity of a sub n plus 2 times n plus 2 times n plus 1 z to the n, right? And now that we have that, we can put this way back up into, sorry if we're keeping track, this is the actual equation that we're solving for. If we sort of replace this for this first term, we get something that kind of looks a bit nicer, right? We have the sum over n, and we're summing from 0 to infinity of all of these terms. So a n plus 2, n plus 2, n plus 1, z to the n, and then, sorry, scroll down a bit, the rest of these terms minus a sub n times n minus 1, z to the n, minus 2 a sub n z to the n, plus a sub n z to the n, all equal to 0. if we factor out that z to the n, this whole thing, let me see if I can write this a little neater. Sum over n times a sub n plus 2, n plus 2, n plus 1, minus a sub n, n minus 1, minus 2, a sub n times n plus a times a sub n, all multiplied by z to the n, has to be equal to 0. Now, for this to be true for all powers, for all z, essentially these coefficients have to be equal to 0, right? All the coefficients must independently add to 0. So we're left with sort of a useful equation, a n plus 2, n plus 1, minus a sub n times n minus 1, minus 2 a sub n times n plus a times a sub n has to be equal to 0 to solve for this. This essentially gives us our equation that we need to solve to get our a sub n's. To do that, we're setting this whole thing to 0. We're leave the n plus 2 term on this side, plus 2, n plus 1, and that's going to be equal to a sub n, n times n minus 1, plus 2 a sub n times n minus a sub n. Simplifying that right-hand side, we get a sub n times n, which we factor out, and then we have n minus 1 plus 2 minus a sub n. This ends up being n plus 1, divide by this side. We get the recursion relation, a n plus 2 is equal to a to the n times n plus 1 minus a. I've messed up my brackets here. No, that's right. Divided by n plus 2 and n plus 1. So this gives us a recursion relation that sort of answers how we get each a sub n in our power series solution for that p sub z is equal to sum over n equals 0 to infinity of a sub n z to the n. And that, so this tells us our function. If we can figure out these n's, we have the recurrence relation relating them all. We can look at this and essentially split it up into even and odd terms. So if we look at even n, we know that a to the 2, the second constant is just going to be a 0 times 0, 0 plus 1 minus a all over 2, or this ends up being negative a over 2 times a naught. And if we go to a to the 4, this ends up being a to the 2 times 2 plus 1 minus a all over 4 times 2, or 6 minus a over 12. This, and if we substitute in a over 2, which we got here, times a over 2 a naught. I think I may have made a sign error in here, but yeah. So we've got this sort of recursion relation that gets us those. Looking at the odd terms in this series, we have a3 is going to be equal to a 1 times 1 plus 1 minus a all over 3 times 2, which simplifies to 2 minus a all over 6 times a1. And then, a5. Going through all that, plugging it in, you end up with 12 minus a. And then if you plug in what that a3 is as well, 2a over 20 times 6 times a1. But the point is, this recursion relation, we can figure out all the powers of this term. These sort of not yet determined a1 and a0 are actually set by normalization. Remember that this function has to be normalized. So that will determine a0 and a1. And the recursion relation determines all the other coefficients in that power series. And we've got our P sub z that will look like this. P sub z is going to be equal to a0 times z to the 0 minus a over 2 times z squared plus dot dot dot. In the odd terms, a1 times z to the 1 plus 2 minus a over 6 z to the 3 dot dot dot. Right. So we have that function, and we've almost sorted out everything we need to sort out. The last thing we have to sort of take into account is essentially this function has to be normalizable, which means this series that we sort of that we've derived, these coefficients, they have to converge, right? And if we look at our recursion relation, right, we have n plus 1 or n plus 2 rather is equal to a n times n plus 1 minus a over n plus 2 times n plus 1. Right, this is our recursion relation. If we look at the limit of large n, so we're taking that sum to the end, we get an plus 2 over an. This is equal to n squared plus n minus a over n squared plus 3n plus 3. For large n, these n squared terms just dominate. So for very large n, this is, kind of goes towards 1. So in that infinite sum over n, we're going to have a bunch of 1 plus 1 plus 1. This doesn't converge if we go to n. So we have to sort of truncate the sum to some n max, right there. We have to truncate this series for it to be a valid normalizable solution. And to do that, we essentially say, well, okay, if there's some n max, then the an plus 2 above that is going to be 0, right? It's the terms above that n max are going to be 0, which amounts to taking this numerator here and setting it equal to 0. So we have n max times n max plus, n max, plus 1 minus a is equal to 0, or n max times n max plus 1 is equal to a, where this should sort of look familiar to us, right? If we recall, we've kind of used this this n, some positive integer. This looks a lot like L plus 1, L times L plus 1, which we've seen before. If you recall, we've used this sort of L squared operator acting on our wave function, had the eigenvalue of L plus 1 h bar squared times that. So what we've just really done, as long as we, identify this maximum sort of termination index as that L, we know that that separation of variable constant in our differential equation sort of sets what that termination index is, and this is ultimately going to be that I help us determine that eigenvalue for our L squared operator. If we look at our power series solution for a given one of these L's or N maxes, whatever you want to call it, we get a polynomial of the degree L, right? So this L sets the degree of that polynomial. Turns out these are called the Legendre polynomials, and they can be just written in terms of what's called the Rodriguez formula, and it's that polynomial is equal to 1 over 2 to the L times L factorial times the Lth derivative, d dz to the L of z squared minus 1 to the L. Right, so this is Rodriguez formulas. It can be used to derive the Legendre polynomials, which are what we've just derived essentially. Those power series solutions up to with the expansion n max equal to L gives us those. The first few terms of those polynomials look like this. Selecting the conventional coefficient and all that. And again, you'll notice that the L, it's a polynomial of degree L. Another thing you'll notice is that for L even, the function is even. For L odd, the function is odd. And another thing we'll notice is these are actually orthogonal functions, right? If you integrate over all space for all z of any of these two things, you get either 1 or sorry, you get 0 if it's not, if L isn't the same for both two functions you're integrating over. Sorry, I got a bit tongue-tied there. And we expect that, right? Because these are solutions to a Hermitian operator, so we expect them to form an orthogonal set of vectors or functions. Continuing to sort of trudge along through this solution, as maybe in depth as that was just solving for the m equals 0 case, right? If we think back to our differential equation we're solving for, we can now look at sort of a general case. If you remember, our differential equation looked like this: 1 minus z squared, the second derivative with respect to z, minus 2z, that look like a 2z dz, plus that a we can now write as L plus 1 because that's our what we just showed, minus m squared over 1 minus z squared. All of this operating on our function is equal to 0, right? Turns out, this is a pretty complicated thing to solve. You do another series solution. We're not going to go through all that. The gist is the solution to this are the associated Legendre functions, and they can actually be derived from the Legendre functions, right? So the associated Legendre function, turns out it doesn't matter if m is positive or negative, so we're just going to leave it as positive and note that these two are equal. But these associated Legendre functions are equal to 1 minus z squared to the m over 2 times the mth derivative with respect to z of our Legendre polynomial. The ones we just sort of derived here. Now, one of the things we can notice here is we just discussed how the Legendre polynomials, p to the L of z, is a polynomial of the Lth degree, right? So if we take the mth derivative of it for m, if m is greater than L, this derivative term is equal to 0, so this function goes to 0. So what we've essentially shown is that the value of m has to be less than or equal to whatever our L is, right? So keep that in mind. But if we run through this these derivatives and do all that, this we can actually get this looks like 1 over 2 to the L factorial 1 minus z squared m over 2 the m plus L derivative with respect to z of 1 z squared minus 1 to the L, right? So if we plug in what our Legendre polynomials in, we get there, and remember our m is less than L. So that means is m can run from negative L to negative L plus 1, dot, 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 through 0, dot, 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 to L minus 1, all the way up to L. We only have those for a given L, we only have those possible values of m. And again, this sort of makes sense. We've been using these operators before, these angular momentum operators, where L squared operating on some wave function gives us the eigenvalue L plus 1 h bar squared, and the z component of that was equal to m h bar times that function. And we had this same sort of restriction where m could run from negative L to L in integer steps in that. This was what we had when we were looking at the spin angular momentum. So we're sort of deriving all of these eigenvalue equations in the position basis with that. And we've got our associated Legendre functions here that give us the position wave functions of this polar part, right? We have to sub back in the fact that our z is equal to cosine theta, but then we have our solution. Some properties of note of these functions, right? So we've already sort of discussed PLM of z is equal to 0 if the absolute value of that m integer is larger than L. That's what limited the values of m. We also noticed that the sign of that m integer does not matter. So we've kind of taken to using m in these equations as being some positive integer and just acknowledging that if we throw in a negative sign, it doesn't change the function. We also, another property is that evaluated at plus or minus 1, these are equal to 0, right? This, you can actually see this just from this term here, right? Plug in plus or minus 1, we get 0 there. This is equivalent, if we think about what our z is being cosine, this is the sine theta at the poles of our space end up being 0. Under parity, another useful property to think about is that P L to the m of negative z is actually equal to negative 1 L minus m P to the L m times z. And lastly, if we integrate these from negative 1 to 1, P L M Z times P Q, different one, M Z dz. This is equal to, it doesn't equal 1, it equals 2 for 2 L plus 1 times L plus m factorial divided by L minus m factorial times the delta function of L and Q. So they are orthogonal unless L and Q match. We're doing the same associated Legendre function here, we're going to get 0. If they are the same, they don't equal 1, they equal this. And this is going to be important when we try to normalize, when we look at what our normalized eigenfunctions are. If you think about what normalization is, you know, take our wave function and integrate it over the entire volume. But in this three-dimensional space and spherical coordinates, this is going to be, for our eigenfunctions with the separation of variables, we're going to have r times r theta, theta, phi, phi, sorry, squared, theta, theta, phi, phi. I guess technically these are the conjugates. Sorry, the volume element is isn't just simply d theta or d phi. It's r squared sine theta dr d theta d phi. If we look at just the phi terms in this, we're going to get the integral from 0 to pi of our polar sort of function here, which depends on L and M theta. We'll use Q and M theta sine theta d theta. That's going to, we're going to want that to be equal to 1 or the delta Q there. And that means our normalized angular functions, polar functions, are going to be, look, like this. It's going to be equal to -1 to the m times 2l plus 1 over 2 times l minus m factorial over l plus m factorial times our associated Legendre functions of our variable, which is cos theta. And this is, we're using that m as a positive integer here, and it's just, it doesn't change. If we look at the negative values of m, it takes the absolute value when we plug it in here. So to recap what we've done, we've taken our relative wave function and split it into radial and then polar or angular components, and now we've solved for the azimuthal part, which was that 1 over root 2 pi e to the I m times phi, and now we've solved for that polar part as well, L to the m theta, which was equal to -1 to the m 2l plus 1 over 2 l minus m factorial over l plus m factorial times these associated Legendre polynomials as a function of cosine theta, right? And we showed that this m is an integer that could range from -l to -l plus 1 dot 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 all the way through 0 up to l minus 1 or l. And that's what we got. And putting these together, we got our, putting them all back together to our angular portion of our wave function. We can write this way, and it's -1 m plus the absolute value of m over 2 times square root of 2l plus 1 over 4 pi l minus the absolute value of m over l plus the absolute value of m, both factorial, all square rooted, times those associated Legendre polynomials, functions, times e to the I m phi, right? So this is what we're looking at for our angular dependence of our hydrogen wave function. Um, the first few terms of these look something like this for given L's and M values. And these, have a lot of the properties we expect from from eigenfunctions of any Hermitian operator. But one big one is they're orthonormal, which means, if I integrate over all space in terms of these angular components, y L1 M1 complex conjugate of that theta phi times y L2 M2 theta phi sine theta d theta d phi. This is going to be equal to either 1 or 0, right? And it's going to depend on if L1 and L2 are the same and if M1 and M2 are the same, right? If either of those are different, we get 0. They both have to be the same. And this is a normalized function that gives us 1. They're also complete, right? So this is, orthonormality. They're orthonormal. They also form a complete set, right? They have completeness, which means any angular part of our wave function can be written as a sum over all of these. So from L equals 0 to infinity, and then the m's can go from negative L to L over some coefficient. You're just linearly expanding these wave functions, these spherical harmonics. We can write any wave function in terms of a linear combination of these spherical harmonics. This is with, and those coefficients for each of those terms is just a projection onto those functions of our state function, or if we were to calculate that in position space, it's the overlap integral between those things. 0 pi y L M theta phi times our wave function, theta phi sine theta d theta d phi. And again, this sine theta term, this all comes from, we're in spherical coordinates, and that volume element is r squared sine theta d theta d phi. So we're looking at the angular part of this element, or the solid angle of that. So we get this sine term. But yeah, they have orthonormality, they're complete. And the last thing that might be useful to look at is parity, right? Which is essentially, if you recall, parity is if I take, this function at some r and I evaluate it at negative r, what do I get? It's entirely determined by L, right? If I take y L of m of theta pi minus theta, and phi plus pi, which is, an r in the opposite direction, just if you can see that. If I have x, y, and z, and some vector r at theta and phi, and I want to make that so it's sticking back and into the page negative r, right? I can go to a polar angle of pi minus that theta gets me to that angle, and my azimuthal angle would be at this phi plus an entire phi up there, because we would project it to there. So this is actually what you get when you invert r. Anyway, sorry, that is equal to negative 1 to the L of whatever the function is at theta and phi, right? So the parity on switching r from positive to minus is determined by this L. If you have an even L, it's even parity. If you have an odd L, it's odd parity. And that's where we are. We've sorted out our angular component of our wave function right here. And now we're ready to sort of take the next step and look at the radial component of that, which will also include the energy of our eigenfunctions, and we'll have a nice, sorry, the full energy eigenfunctions for our hydrogen atom.